How long do you think it takes to build a house for a family that just lost everything in an earthquake? A few weeks? A couple of months? Maybe half a year if you're working in one of the most remote and hostile environments on Earth. In January 2025, China did something that redefined the entire concept of emergency construction. In just 24 days, they erected 733 foldable houses alongside nearly 10,000 tents and sheltered over 47,000 people at an altitude of 300 meters, higher than most commercial airplanes fly, in temperatures dropping to -15 degrees Celsius. And here's the part that sounds impossible. Each house was assembled in 8 minutes, not 8 hours, 8 minutes. A truck arrives. Workers unfold a steel structure the size of a shipping pallet, lock the walls into place, secure the roof, and walk away, leaving behind a fully equipped residence with beds, bedding, windows, a door, and a heater already installed. This wasn't a tent city. This wasn't a refugee camp with tarps and makeshift shelters. This was an industrial-scale housing deployment that turned humanitarian relief into a precision manufacturing operation. But how did they actually do it? How do you transport, assemble, and deliver thousands of houses to one of the highest and coldest places on the planet in less than a month? And what does this reveal about the future of construction, disaster response, and the way we think about housing itself? Let's break down the full processes, from the moment the earthquake hit to the day the last family moved into their new home. On the morning of January 7, 2025, at exactly 9:05 a.m. local time, a massive earthquake struck Dingri County in Shigatse Prefecture, deep in the Tibet Autonomous Region. The China Seismic Network Center recorded the magnitude at 6.8, while the United States Geological Survey classified it at 7.1. The epicenter was just 10 kilometers below the surface, which meant the shaking was violent, concentrated, and devastating. In the hardest-hit villages, 80% to 90% of all buildings collapsed within seconds. Entire communities were reduced to piles of rubble, stone, and timber. The official Chinese report recorded 126 deaths and 188 injuries, though independent Tibetan sources suggested the numbers were higher. More than 3,600 homes were completely destroyed. Thousands of people were left exposed to the elements at 4,300 meters above sea level, where nighttime temperatures plunged to -15 degrees Celsius. At that altitude, oxygen levels are about 40% lower than at sea level. Physical exertion becomes exhausting. Breathing is harder. And when you've just lost your home, your belongings, and possibly family members, the cold becomes a second enemy as lethal as the earthquake itself. Traditional disaster relief, karmets, blankets, and temporary shelters can keep people alive, but barely. Hypothermia, frostbite, and respiratory illness become immediate threats. Within hours of the earthquake, the Chinese government activated an emergency response protocol that had been in development for over a decade. This wasn't the first major earthquake China had faced, and lessons learned from previous disasters, especially the 2008 Sichuan earthquake that killed nearly 70,000 people, had fundamentally changed how the country approached post-disaster reconstruction. The first trucks began arriving within 24 hours of the earthquake, but these weren't carrying sandbags, medical supplies, or tarps. They were carrying something most disaster zones have never seen: prefabricated, foldable housing units designed specifically for rapid deployment in extreme conditions. Each unit arrived compacted, occupying roughly the same space as a standard shipping container. The walls, roof, floor, and structural frame were all factory manufactured and pre-assembled into a folding configuration. Inside the factory, before the unit ever left for Tibet, workers had already installed insulation, electrical wiring, beds, bedding, and a heating system. The units were designed to unfold like origami. Walls hinge outward, the roof locks into place, and the entire structure becomes rigid and weatherproof in minutes. This wasn't improvisation. This was industrial preparedness. The factories producing these units weren't built in response to the earthquake. They had been running for years, supplying foldable housing to construction sites, mining camps, and infrastructure projects across China. When the earthquake hit, The production lines simply redirected their output. The trucks that normally delivered worker housing to remote construction sites were now carrying those same units to Tibet. According to official Chinese data, the logistics operation involved hundreds of trucks operating in coordinated convoys. The routes into the disaster zone were challenging: narrow mountain roads, damaged bridges, and icy conditions. But the trucks kept moving, delivering load after load of housing units to pre-designated assembly sites. Once the trucks arrived at the disaster zone, the real speed became visible. A small team of workers, usually 4 to 6 people, would unload a single housing unit from the truck bed using a forklift or crane. The unit, still in its folded configuration, was placed on a prepared foundation pad, which in most cases was simply a flat, cleared area with gravel or compacted earth. Then the assembly began. Workers unlocked the hinge mechanisms on the walls and extended them outward. The walls, already fitted with windows and insulation, clicked into place using a locking system similar to industrial shipping containers. The roof section, which had been folded down during transport, was lifted and secured to the wall frames. Workers used power drills to drive steel bolts through pre-drilled holes, locking the structure together. Inside, the beds were already mounted to the walls. The bedding was already packed in storage compartments. The heating unit was already wired and ready to plug into a power source. In some cases, portable generators were used. In others, temporary power grids were set up to supply electricity to clusters of houses. From the moment the unit touched the ground to the moment it was ready for occupancy, the process took 8 minutes. Not 8 minutes per worker, 8 minutes total, start to finish, with a small crew working together. This assembly speed wasn't an exaggeration or a propaganda claim. It was the result of precision manufacturing and deliberate design. Every component was pre-fitted, pre-tested, and pre-installed. There was no cutting, no welding, no mixing concrete, no waiting for materials to dry. The construction site had been moved into the factory, and the work at the disaster zone was simply final assembly. One house in 8 minutes is impressive, but 7,733 houses in 24 days is a logistical operation on an entirely different scale. To understand how this was possible, you need to understand how China organized the deployment. First, the work never stopped. Teams operated in rotating shifts, 24 hours a day. While one crew assembled houses during daylight, another crew prepared foundation sites, unloaded trucks, and organized materials. At night, portable floodlights illuminated the work areas, and the assembly continued. Second, the work was parallelized. Instead of building one house at a time, dozens of crews worked simultaneously across multiple sites. The disaster zone was divided into sectors, and each sector had its own assembly teams, supply trucks, and logistics coordinators. As soon as one house was completed, the crew moved to the next foundation pad and started again. Third, the supply chain was continuous. Trucks didn't wait for orders. They were dispatched on a rolling schedule from factories across China. As soon as a truck was unloaded, it returned to the factory for another load. The factories operated at maximum capacity, producing and shipping units as fast as they could be assembled. By the end of January, just 24 days after the earthquake, 733 foldable houses were standing in the disaster zone. Alongside them, 941 tents had been erected for temporary overflow housing and communal facilities. Together, these shelters accommodated 787 people, essentially the entire displaced population of the affected area. It's important to understand what these houses actually were. They weren't tents with rigid frames. They weren't plywood shacks. They were insulated, weatherproof, structurally sound housing units designed to withstand earthquakes, high winds, and extreme cold. Each unit measured 18 square meters, roughly the size of a small studio apartment. The walls were constructed from galvanized steel frames with insulated panels, providing thermal protection in sub-zero temperatures. The roof was sealed and waterproof, preventing snow and rain from entering. The floor was elevated to prevent moisture infiltration from the ground. Inside, the heating systems were critical. At 4,300 meters above sea level, nighttime temperatures regularly dropped below -15 degrees Celsius. Without heat, even a structurally sound shelter could become a death trap. The heating units installed in each house were designed to run on either electricity or portable fuel, ensuring residents could stay warm even if power supplies were interrupted. The units were also designed to accommodate up to 8 people, making them suitable for extended families or groups of survivors who had been displaced together. Beds were built into the structure, and storage compartments provided space for personal belongings, clothing, and supplies. From an engineering perspective, these houses were designed to last. Unlike canvas tents that degrade in weeks or months, the steel-framed units could remain functional for years. This meant that while permanent reconstruction was underway, residents weren't living in gradually deteriorating shelters. They were living in stable, safe housing that could serve as transitional accommodation for as long as necessary. But the foldable houses were only the first phase. Even as the emergency shelters were being deployed, China was already planning the permanent reconstruction. According to the state portal china.org.cn, the reconstruction program delivered more than 32,500 houses across 486 villages in 7 counties in less than 10 months. Of that total, more than 22,000 residences were built from scratch, and another 10,500 received structural reinforcement to withstand future earthquakes. Essentially, the entire housing stock of the disaster zone was replaced or upgraded within a year. The reconstruction involved 134 construction companies, 61,000 workers, more than 2,600 managers, and approximately 6,600 pieces of heavy equipment. The work was carried out at an average altitude of over 4,000 meters, reaching as high as 300 meters in some locations, higher than any permanent settlement in North America or Europe. The conditions were brutal. Workers faced low oxygen levels, extreme cold, and unpredictable weather. Materials had to be transported along narrow mountain roads. Foundations had to be anchored into rocky, unstable terrain. Yet, despite these challenges, all residences were delivered within the announced schedule. So how did China build this capacity? The answer lies in more than a decade of investment in prefabricated and modular construction. The foldable houses used in Tibet weren't invented in response to the earthquake. They were already being mass-produced for other purposes. China's prefabricated construction market is valued at approximately $1.62 trillion and is growing at nearly 10% per year, a rate that doubles the global average. Industry projections suggest the sector will reach $2.47 trillion by 2029. This industrial scale means that the capacity to produce thousands of housing units in short timeframes already exists. It just needs to be redirected. The factories producing these units are located across China, from coastal industrial zones to inland manufacturing hubs. They operate like automotive assembly lines, with standardized components, quality control checkpoints, and automated production processes. The same factories that supply worker housing for railway construction, mining operations, and infrastructure projects can instantly pivot to disaster relief when needed. And the technology is being exported. The China Railway Group has already shipped 1,000 sets of prefabricated materials to Kazakhstan in a contract worth approximately $4 million. CSEC, considered the world's largest contractor by revenue, received the first Chinese modular construction approval in Dubai and plans to deliver 50,000 housing units per year in countries participating in the Belt and Road Initiative. The Tibet operation left a message that disaster response agencies around the world couldn't ignore. When the next major earthquake hits a populated region, and it will, the country with a factory system ready to redirect housing production will save more lives than the country that tries to assemble a response from scratch. Traditional disaster relief relies on tents, tarps, and temporary shelters that offer minimal protection in extreme cold environments, at high altitudes, or in regions with prolonged displacement. These solutions are inadequate. Heated, insulated, structurally sound housing units completely change the survival equation. The question for engineers, civil defense managers, and governments worldwide is no longer whether prefabricated construction can compete with traditional methods. The question is how quickly other countries can adopt a system that, in a remote region of Tibet, proved capable of replacing the entire housing stock of a devastated area before the end of the first winter. The Tibet deployment is part of a broader transformation in how China approaches construction. The same industrial principles that enabled 733 houses to be built in 24 days are being applied to urban housing, commercial buildings, and infrastructure projects. The advantages are clear. Factory production ensures consistent quality, reduces construction waste, shortens timelines, and allows for better control over materials and labor. Components can be inspected and tested before leaving the factory, reducing the risk of defects that are difficult or impossible to fix once a building is completed. But there are also questions. Does building this quickly create places where people truly want to live? The history of prefabricated housing includes both successes and failures. Post-war housing projects in Europe and the Soviet Union solved immediate shortages, but often created monotonous, poorly maintained neighborhoods that deteriorated over time. China's current approach attempts to address these concerns by combining industrial efficiency with improved design, better materials, and stronger quality control. The foldable houses used in Tibet were functional and utilitarian, designed for emergency use. But the permanent reconstruction that followed included more variety, better finishes, and community planning. The bigger challenge is scalability. Can other countries replicate this system? The answer depends on industrial capacity, government coordination, and the willingness to invest in manufacturing infrastructure that may sit idle until the next disaster strikes. For China, the investment makes sense. The country faces regular earthquakes, floods, and other natural disasters that require rapid response. For other nations, the calculus may be different. So here's the question. If a system exists that can shelter 47,000 people in 24 days, in one of the harshest environments on Earth, using houses that assemble in 8 minutes and can last for years, should every country be investing in this technology? Or is this a uniquely Chinese solution, enabled by industrial scale, centralized planning, and a manufacturing base that most countries simply don't have? Let us know your answer in the comments below. And if you found this breakdown fascinating, don't forget to like, share, and subscribe as we continue exploring the engineering projects and technologies that are reshaping our world in ways few people ever imagined. See you in the next video.